All right, welcome back to part 2 of our example problem for composite beam analysis. And so far, we've transformed the area and calculated some geometric properties of this new eye-shaped transformed section. And now what we're going to do is calculate some stresses. I've drawn the section down here again later for drawing the stress profile later. But really now what we want to do, this is number 3. Step 3, if you will. 3 here is calculate normal stresses for the transformed section. Transformed section here. And really, because we've transformed this all into one material, we can use our flexure formula minus my over I. And so the stress at the top, so our maximum stresses are here. This is a symmetric cross section, so really our maximum normal stresses due to a moment right here like this is compression at the top, tension at the bottom. And so here, I'm going to erase that because we know it's compression at the top, tension at the bottom here, and I need that space later. But here, the sigma top, sigma, or the stress at the very top here, is equal to minus my over I. And here, in this case, that moment, the maximum moment at midspan of the simply supported beam was 100 kilonewton meters. The distance from the neutral axis to the top is 175 millimeters. I want to convert all my units, especially the meters, into millimeters. So 1,000 millimeters per meter divided by the moment of inertia, which was 3.504 times 10 to the 8th millimeters to the 4th. And what that gives me when I run this calculation is minus 0.05 kilonewtons per millimeter squared. And I like keeping things in terms of kilonewtons and millimeters, or keeping the distance or the lengths in millimeters, just because I know 1 kilonewton per millimeter is also the same as 1 GPa. So this is the same as minus 0.05 GPa. Or in megapascals, it would be minus 50 megapascals. And then because I have a symmetric cross section, I know that the stress at the top is really the same magnitude at the bottom. So sigma bottom is going to be, instead of compression, it'll be tension. So it's going to be a plus 50 megapascals right here. And so if I want to draw the stress profile of this section here, so here, let me stress profile in this section. So let me draw some lines indicating the top and the bottom here of this transformed section right here. It is here, this transformed section that's all steel. I have, let's see, neutral axis location right about here. So let's go with right there, neutral axis. And I have compression at the top right here. So bam. Here, this will be minus 50 or 50 MPa causing compression. So I draw the arrows compressing that surface like this right here. And this point is sigma top of 50 megapascals. Sigma top is equal to that. And at the bottom, I'm causing tension on the surface. So here, I point about right there. Bam, like that. And I have here, like this, and this right here is the stress profile for a section with all of one material. And this would be sigma bottom in tension equal to 50 MPa as well. And really, what if you've been familiar with this topic before, to go from the transform, the next thing we want to do is go to the composite section now and draw the stress profile for the composite section. And really, what you've observed before is that in order to go back to the composite section, so here I have to go to the composite section. Really, this point right here, right where my material transitions from steel to wood is really important right here. So let me, in terms of my transformed section, let me calculate these two stresses here, and I can do that just by similar triangles, which is here I have this distance right here, which was 175 millimeters, and so this location right here at the transition, so I'll just call that like sigma 1 or something. And sigma 1 sigma 1 is equal to sigma 1 over this distance right here, which is 125 millimeters. Sigma 1 over 125 millimeters is equal to sigma top over 175 millimeters, because the variation is linear, and that means that sigma 1 is equal to, oh gosh, I don't know, what is that? That's going to be some number which is 36 megapascals right there. Okay, so 36 megapascals. I could, okay, so now that with that, and that's the same thing down here, I have right here, this other point right here is also 36 megapascals right here, right where I transition from this point right here in the flange to the quote-unquote web, which is wood transformed into steel. To draw the strain profile, I just had to divide every single number here by the modulus of elasticity of steel. And so here at the top, if I want to calculate the strain at the top, so here, let's see, let me call this step 4, strain profile. Strain profile right here. Bam, like this. So we're kind of going this kind of a roundabout way, but you'll kind of get the point after you see what's going on here. The strain profile here, the strain here, the strain at the top, if I want to calculate the strain at the top, I just have to take sigma top divided by, because all this material is quote-unquote steel, I just divide by the modulus of elasticity of steel. So that would be, mine is equal to, right here, what is that? Equal to 50 MPa negative divided by 200 GPa, which is, this is just 0.05 GPa right here. This whole thing becomes negative 0.00025 strain. Okay, and that just means the negative just indicates I have a compressive strain, and just by symmetry, I know that the strain at the bottom is also a positive 0.0025 strain, okay, or millimeter per millimeter, whatever units you want to use. And the strain right here, where the material transitions between steel and wood, that's going to be just sigma 1 divided by E steel, which is, in this case, 36 MPa, divided by 200 GPa, which ends up being, this is same as 0.036 GPa, in case you were wondering. This whole strain, epsilon 1, is negative, at this point right here, negative 0.00178, indicating, again, compression. And so if I want to draw the strain profile, let me write this up here. Negative 0.000178 strain. And don't forget, the stress was in compressive stress, so that's why I have the negative there. But here, now if I want to draw the strain profile, so here of the transformed section, or the transformed area here, let's see, let me draw a vertical line. Bam. So using Hooke's law, all I did was divide all the stresses by the modulus of elasticity of steel. And I have the neutral axis. The strain at my neutral axis is 0. And I have a linear strain profile. I say all the strains on the right are considered negative or compressive strains. So right here, this is that 0.0025, 0.00025, and here's my positive or tensile strain of 0.00025 right here. And then the strain where the material transitions in from one to the other is 0.0000178 strain. And I would have the same value here wherever I transition, but in tension, this would be this 0.0000178 strain. And now, last but not least, to draw, where did it go? Now I want to draw my composite section. So my composite section right here, so get some space right here. My composite section, I want to bring everything back. My composite section, I have the material here like this, And from the strain profile, all I got to do is multiply every region by the appropriate modulus of elasticity, and I will have the stresses in each of the materials or in each of the locations. And I'll just get a stress profile from there. And so here is my composite section. This was the steel. This is the wood. Oops, the wood. This is the steel. And my dimensions here, just real fast. Give me a second. Bam, bam, bam. Only 50, 250, 50, and this width was 150 millimeters. All these units are millimeters, so millimeters. Oh, that's sloppy. Okay, but here, I got the steel, wood, and steel. My strain profile hasn't changed, so just to emphasize that point, I'm going to redraw my strain profile here. This strain profile between the transform section and the composite section is still the same. So here I got this, and I have here the neutral axis location right here, and my strain profile, and this value here still 0.12325, 0.00025, and 0.00025. Compression at the top. The strain here is 0.123178 strain right there. And now I just multiply by the modulus of elasticity of each, and to get the stress profiles for the composite section. So everything in the flanges at the tops and bottom, I'm multiplying by 200 GPa, which tells me that here I have at the top right here in compression, I've got 50 MPa. So that really hasn't changed in compression right here. So this was that negative 50 MPa. Right here to the point where I transition, it's still steel. And so here, this stress value is right here, 36 MPa. And then right below this point right here, right below that line, I transition to wood. So I essentially have this discontinuity. And now I got to take this strain value right here, this strain value, and to calculate the stress in the wood there at this point, I would say sigma wood at that point is equal to the E of the wood times the strain at that point, which in this case is 10 GPa times 0.000178, which makes this 0.001 GPa, which is 1.78 megapascals. Okay, so if you just do the units conversion right here. So really what that means is that my stress right here at the transition of the material, I have this right there at that point, is 1.78 megapascals. And so my stress profile here in compression, I would have here like this, and then I have this arrow right here, and then I continue with the step. There's a neutral axis, right here, whoa. Okay, and here my stress profile goes down from here back to 0, like that. And so, this is my compressive stress profile all the way down to 0 right here. And then and it's exactly, the magnitudes of the values are the same in tension. And so I'm going to have here at some point where I transition from wood to steel, I'm going to have this tensile stress of 1.78 megapascals. So here like that, like this, and then a step or a discontinuity to 36 megapascals right here, and then a linear transition to 50 megapascals in the steel in tension. So 50 megapascals, and here's 36 megapascals, all in tension right here to clean this up right here. And I've really beleaguered this point a little bit more than I needed to. But here, check this out, right? So this is 36 megapascals, 50, 1.78, all this stuff right here, okay? So we have this right here. So our answers would be that the maximum stress in the wood is 1.78 megapascals, and the maximum stress in the steel is 50 megapascals. Now, you don't have to draw the strain profile all the time. And if you look at this relationship here, look, to calculate the strain at let's say right here at this, or let's say to calculate the strain at this point right here at epsilon 1, what we did was we took the we said the stress, in the steel divided by E steel is equal to a strain value. And then later on, to get the stress of the wood, move, don't freeze, please. Okay, this right here to get, so we have this right here, and then to get the stress of the wood, we said E of the wood times the strain is this is how I get my stress in the wood. So if I substitute this right into here, that just tells me that to convert back into the wood stress, if you will, then all I got to do is use this modular ratio of EW over EST times the actual stress in the transformed material, all the material transformed into steel. And this is my relationship, okay? So I could have just modified all these stress values by the modular ratio, EW over EST, to clean up this stress profile where I have actually wood. All right, and this would have been my stress profile. Okay, so this was a little bit more detail. Normally, you're not asked in problems to draw the strain profile, but drawing the strain profile is really useful, especially if you do any kind of like experimentation, because really most of the time, all you have to measure stuff are strain gauges and transducers, displacement transducers. So, and the strain gauges are used the most in terms of just taking measurements off of a structure or a material. Okay, hopefully that was insightful. Let me know if you have any questions, and enjoy.